Hello, everyone. This is the class material that would have been covered on Thursday, April 16th. Amazing how far we've come, isn't it? Filming this from my house again. I've been joined by my dog, Snoopy. Say hi, pup. There he is. Just lazing around on a lazy afternoon. What a dog's life. Hope you are all still well. Hope you're all safe. Hope you're all healthy. Hope you're all practicing social distancing, as I am. I'm doing well, still healthy, family's healthy, dog's healthy, life's pretty good. This has been end of week 4 now for these online classes. I haven't gotten a lot of feedback from everybody, which I assume is a good thing. If there is anything that you need, if there is any thing that I can do that will help make this process easier, please let me know. I'm here to help. So let's get to it. We are continuing talking about the Milky Way galaxy. So let's get to today's review question. There it is. Today's review question is, halo stars on average are blank than disk stars. We did this at the end of class last time. Halo stars, also known as POP2 stars, population 2 stars, disk stars, also known as population 1 stars. Are halo stars older and more metal rich, younger and more metal rich, older and less metal rich, or younger and less metal rich? I'll let you, you can probably just look it up if you want to. But if you'd like to make a guess, sure, write it down and then we'll go over it. Pause if you want. Okay. So halo stars are in the halo of the galaxy, disk stars in the disk of the galaxy. That's not that complicated. The halo stars formed first. All the present star formation in the galaxy is happening in the disk. So halo stars are all old stars. They're all more than 8 to 9 billion years old. And disk stars are all pretty much younger than that, younger than about 10 billion years old. And so halo stars are much older on average than the disk stars. So that narrows it down to A or C. On the metal rich variety, we talked about this at the end of class last time. Halo stars having formed earlier in the universe when there were less heavy elements around are less metal rich. And when I say metal, astronomers do not agree with chemists on this fact. To an astronomer, a metal is anything element that is more massive than helium. To astronomers, things like neon and argon are metals, even though to a chemist, those are the least metal things you can possibly think of. But that's besides the point. That's what I mean by metal rich, though. Here. So the answer is C, they are older and less metal rich. Great. This is a cool video. I can show you a little bit of it, although it's crazy to have you watch a YouTube video inside a YouTube video. Is that even possible? Is that going to create some sort of time warp? I don't know. Let's give it a try. I'll show you a little bit of it anyway. Do I even have it open? Yes, I do. I think I'd be more prepared for these things, but no, I'm not. This is it. Okay, hopefully you're seeing this now. Forgot to share one in the last video. Anyway, this is an actual simulation of the Milky Way galaxy forming. And the only reason I'm posting this, there's a link to the video. You can watch it on your own time. But I like this one because, oh, look, you can see it in my whole browsing. That's fun. I'm not the only one who uses my YouTube account, so it's not just that. Not just me. Anyway, hopefully you're still seeing this. I'm not going to play this whole thing. It's a 2-minute video, but it shows one simulation of how the Milky Way forms. And so how does the Milky Way form? Well, the cartoon version is a giant cloud of gas just falls and collapses together to form a galaxy, and it has some slight angular momentum, and so it settles into a disk, and you get a spiral galaxy. The real story, just like star formation, is much more complicated than that. Probably the seeds of the Milky Way form at some point early in the universe, and it's a series of dozens and dozens of mergers with other sort of massive things in the universe that eventually, I'm going to fast forward this, you get to something that kind of looks like a spiral galaxy, right? But there's still all kinds of stuff floating around, and it's a very complex process. So go ahead and watch that in the supplemental materials for this class. It's an interesting to watch it happen, but we'll stop this there. You can take a look on your own time. All right, where were we? There we go. So was very complex. The actual star formation was not a simple process. Okay, so now our next goal is to weigh the Milky Way galaxy. We need to know how much matter there is, how much mass there is in the Milky Way galaxy. So obviously there's no scale that's big enough to do it. We have to be more clever about how we're going to measure the mass of the Milky Way galaxy. So let's remember some formulas that we've used in the not so distant past. Here's the escape velocity formula. Remember, this is how fast you have to be moving to leave an object and never come back. This is the escape velocity. The escape velocity squared is 2 times g, which are constants, the mass of the object you're trying to escape from, and how far you are from the center of that object. If instead you want to orbit that object in a circular orbit, perfectly circular orbit, it's a very similar equation. The only difference between the circular velocity equation and the escape velocity formula is that the 2 isn't there. It's just g times m over r. You might remember for the Earth, this number comes out to be 8 kilometers per second. That's the speed you need to be getting to orbit the Earth, low Earth orbit. This is more like 11 kilometers per second, the speed you need to physically leave the Earth's orbit and never come back. And so it's the same formula, it's just the 2 is missing. And so this gives us an interesting opportunity because we've used this, or we could use this to calculate the circular velocity if we know the mass and the radius. But if we know the circular velocity and can measure it, and know the radius, how far we are away from the center of that thing, we can turn this around and get the mass. And that's the game that we're going to play to measure the mass of the Milky Way galaxy. So let's just do some algebra first. Here's my trusty whiteboard. Here is the formula we started from. The circular velocity, I'll just label it v sub c, is gm over r. We want to know what m is. Let's solve this for m. Let's get rid of the g on both sides. Multiply by 1 over g. And get rid of the r on both sides. We can just multiply by r on both sides. Multiplying both sides by r over g, the r's cancel out over here. The g's cancel out over here. And we get m, the mass, is equal to v circular squared times r divided by g. That's it. If you can measure how fast you're moving around something, and you can measure how far you are away from the center of that something, then you can calculate its mass. In fact, this is how we know what the masses of the planets are. For the most part, if they have moons, it's very easy to calculate how fast the moons are going around it and how far away they are from the center. And that gives you the mass directly. Okay, let's go back to slideshow. There we go. And this next slide is, guess what? I've just done exactly that. I've solved it for you. mr equals r times v squared over g. So let's define these things briefly. And I'll tell you the caveats. So let me go back to my whiteboard. Okay. I'm going to call this M sub r, and there is a reason for that. This is not necessarily the total mass of the object that you are orbiting. It is, in fact, the mass of object you are orbiting within the radius of your orbit. I'll just say r, within r, the radius of your orbit. R is the radius of your orbit, how far you are away from the center of that thing. And V is the orbital speed. We could call that VC, the orbital or circular velocity. Now, you know, for something orbiting like the sun or like a planet, like a moon, these speeds aren't going to be constant, right? If you have a highly elliptical orbit, it's going to be moving faster when you're closest to the center and slowest when you're out on the edge. This VC is the orbital speed that you would have if you were in a perfectly circular orbit. And so if you're in a perfectly circular orbit, you're never changing your distance from the center, and therefore you're never changing your speed. And so that's what this V is that we're talking about. Now, for the Milky Way galaxy, we are in a fairly circular orbit going around the center of the galaxy. And so this VC basically just is the speed that we're going around the center of the galaxy in. This is how far we are away from the center of the galaxy. And if we do that, we get the mass of the Milky Way. Almost. We get the mass of the Milky Way that is within the Earth's orbit. And we know that's not the entire Milky Way. It is most of the Milky Way, though. So it's going to give us a fairly good handle on what's going on there. Okay. There I am, I'm back. Okay, so we should answer the question. What is the mass inside the sun's orbit of the galaxy? I think I'm going to come back and solve that in the next video though. So I'll see you there. Stay tuned.